Nestled at the foothills of the majestic Rocky Mountains sits one of Nucor Corporation's various steel manufacturing operations located here in Plymouth, Utah. Welcome to Nucor Steel, Utah. Employing approximately 350 full-time personnel, this facility, known as a mini-mill, we make over 400 different high-quality steel products. Here, our philosophy is based upon the concept of total quality management, where commitment to our customers, safety of our workforce, quality of our products, environmental responsibility, and facility productivity are the cornerstones of our daily routines. This video was created to show you, our customers, or you, our potential customers, just how we go about making our steel products. The description mini-mill is used within the steel industry to describe those facilities which do not use iron ore as their primary raw material in the creation of the finished steel product. Rather, the mini-mill's raw material is aftermarket scrap metal. Thus, essentially here at Nucor Steel, Utah, we recycle discarded waste metals into usable, high-quality finished steel products. Proudly, Nucor Steel, Utah is one of the most cost-efficient steel-making facilities in the world, and as you will see, the mini-mill process is very fast and actually quite simple. First, we must receive and separate the incoming scrap metal. Then we begin the actual processing of the scrap metal into a finished steel product by melting the scrap down. Once melted down, the molten metal is cast into a billet, which is in turn rolled into a finished steel product. The finished steel product is then stacked, bundled, and tied for later warehousing or direct shipping to our customers. Well, now that you've seen the entire process in brief, let's take a moment and discuss each step involved in the recycling of scrap metal into a finished steel product. Scrap metal is obtained through local scrap brokers and is delivered to our facility via large transport truck or bulk rail car. Before each load of scrap metal is accepted at the facility, it is first scanned for radioactive contamination and then weighed. The scrap metal is then graded by its elemental composition and style for on-site storage. For example, some scrap may be higher in its carbon or copper content, or it may be of a shredded, plate, or structural style. Much like baking a cake, making steel takes a recipe. This recipe is based upon the finished steel's alloy composition as determined by the production schedule, which is supplied by our sales department, and of course our production schedule is driven by our customers' requests. Once we select the necessary scrap raw material to begin making our desired product, we load the scrap into large vessels known as charge buckets. Each charge bucket is capable of holding 25 tons of material, not all of which is scrap metal alone. We will also add various fluxing agents which promote the melting process or remove scrap metal impurities, such as aftermarket paints. Once filled, the charge bucket is then used as a means to load each of our 2 furnaces with our scrap raw material, and as you can see, this is done with the use of overhead cranes. First, the electrodes are raised out of the furnace and the roof of the furnace is swung out of the way. Then the charge bucket is positioned over the now open furnace, and when the conditions are considered safe, the bottom of the bucket is opened, releasing its contents into the furnace. This general process is repeated 2 additional times in order to create a volume of molten metal equal to about 60 tons. This amount is referred to as a batch, or more commonly, as a heat of steel. The process of actually melting the steel occurs once the charge bucket has been removed from the furnace area and the roof of the furnace is again closed. The electrodes are then lowered into the furnace, and by creating an electric arc to generate tremendous heat, the scrap metal is converted into molten metal at temperatures in excess of 3,000 degrees Fahrenheit. Our personnel who operate this area are highly skilled and very aware of their individual safety responsibilities. The actual process of charging and then melting a heat of steel only takes us approximately 50 minutes per furnace. This charging and melting sequence is timed in a staggered fashion, such that as one furnace is ready to tap its heat, the other is about halfway through its process. There are several reasons for this staggering, one of which is to maintain a constant, even supply of molten metal to the caster, the next phase of our system. Another is environmentally driven, and it is to allow our baghouse emission control system to keep up with any generations that the furnaces might have. A third is simply that there is only a limited amount of transfer equipment available, and to avoid bottlenecks, we need to stagger the processes. As the scrap metal is being melted, impurities rise to the surface of the molten bath. To assist in this, non-volatile carbon is injected into the molten bath via our automatic lances. At the same time, pure oxygen will also be injected into the molten bath in order to increase the molten metal's heat. As the impurities rise to the top of the molten bath, a frothy mixture is formed. This mixture is referred to as slag, a waste byproduct to us. This waste byproduct is poured off from the front side of the furnace into a slag pit area where it is collected and sold to another on-site company, which processes it and sells it as a road base material. To assist in the removal of the slag, each furnace is able to tilt forward. As you can see, this action is similar to that of a rocking chair, and coincidentally, we refer to our furnaces as rocker-type furnaces. Once the slag is removed, the temperature of the molten steel correct, and the chemistry of the steel acceptable, we tap the furnace. In this process, we tilt the furnace back and pour the molten metal heat into large buckets known as ladles. A common question is, why does the molten metal not melt through the steel furnace wall or ladle side? Well, both our furnace and our ladles are lined with special refractory bricks, which are designed to withstand extremely high temperatures. In addition, the roof and furnace walls are water jacketed. The ladle, holding around 55 tons of molten material, is now transferred to our continuous caster area using huge overhead cranes. In this area, we convert the molten metal into our intermediary, known as a billet. Once the furnace has been tapped, the ladle is transferred into a ladle stirring station, which is located on the side of our caster. At this station, the heat's elemental composition is again checked, and any additional alloys are added. Here also, we inject argon gas down a long nozzle, or argon lance, as we call it. The lance is the pole-like device which is being lowered into the ladle. The action of the argon injection serves to agitate the molten metal, essentially stirring the contents of the ladle. The ladle is now moved from the ladle stirring station onto the top of the caster. The fresh ladle then moves into its release position, and the expended ladle is removed to be refilled back at the furnaces. Once in position, the ladle begins to gravimetrically release its contents into a holding vessel which we cannot see, known as a ton dish. The ton dish serves to spread out the molten metal and release it in a form that we call strands. Our caster has 4 of these strands, as you can see. The ton dish also serves as a means to control the flow of molten metal into each strand mold. Although we commonly refer to this area as the caster, more correctly it should be called our continuous caster. This is more aptly descriptive of our unit, as there is never a break in the flow of molten steel from the ton dish down and out to the formed billet. From the ton dish, each nickel-sized strand flows into its own individual mold. The mold is a copper, water-jacketed, rectangular-shaped device. It is within this relatively cool area that the billet begins to take its form. The newly formed billet works its way down the caster, where we make use of gravity's assistance to make this system work, until it reaches the automatic torch cutting area of the caster. Here each billet has begun to solidify from its outside in, but it still has a small molten core. It is here at the torches that we cut the billet to a product-specific, specified length. Once cut, we allow the newly formed billet to cool somewhat, and then we transfer it to either our billet yard for short-term storage in large stacks of billets, or on occasion we will send the billet right onto our finished product production area, known as our rolling mills. Inventory control begins in our billet yard. Each heat, at approximately 55 tons, is individually marked in order to distinguish it from other heats. And in order to minimize our overall yield loss, each billet's length is carefully controlled to match the finished product requirements of our customers. Nucor Steel, Utah has two rolling mills at this facility, and you will see pictures from both mills. Each mill operates under the same principles, with the basic difference between the mills being the size of the products that can be efficiently run. Physically, the equipment within our number 1 mill is substantially larger than the equipment in our second mill, nicknamed the small mill. The heats of billets are produced in a sequence such that when the roll mill requires billets, they will be available in the necessary production order. As the billet leaves either the caster or billet yard, it enters into either of our two rolling mills' reheat furnaces. Here, the billet is heated to approximately 2,200 degrees Fahrenheit. This reheating process is necessary to be able to form the billet into the desired finished product. Once the billet leaves the reheat furnace, it enters a device known as a descaler. This device shoots high-pressure water onto the surface of the billet in order to remove any oxidation products. The descaled billet now enters the rolling stands of the mill. The function of each stand in sequence is to, by sheer force of pressure, reduce the 6 1/2 inch wide billet down to both the size and shape of the desired product. This sequential size reduction causes the billet to elongate, so a billet which enters the first stand at a speed of around 5 feet per minute may exit the last stand at speeds in excess of 1,500 linear feet per minute. To make the desired product, the rolls of each stand are machined on site. This is where we actually cut individual patterns into specifically matched pairs of rolls. Depending upon the size of the product to be produced, each pair of rolls may have several pattern passes milled into them. Once the billet exits the last stand in the mill series, it enters a shear which cuts the billet into cooling bed lengths. These cut lengths of product now enter the cooling bed where product quality control samples are taken and sent to our quality assurance laboratory for various tests. The function of the cooling bed is just as its name implies. This bed is designed to allow the hot product sufficient time to cool before it enters the finishing straightening area of the mill. The cut lengths of product now pass through the straightener. This unit serves to cut the lengths of product into those actual sizes that our customers may desire. From this point, the product enters the stacker tying area. Here, each bar is counted, put into a bundle, and wire tied. This bundle of product then moves into the tagging area. Within the tagging area, one of our skilled operators affixes a metal tag onto the end of the bundle of steel. This tag is extremely important in our inventory control and product quality assurance program. Each tag is individually barcoded for ease of operation, and it contains the following information: bundle identification number and piece count, product size, length and grade plus, the product's heat number, the production crew's number, and the date on which the product was made. The billet bundle heat information is maintained throughout the production process so that the customer who receives a bundle of finished steel product will have access to the history of both the physical and chemical analysis of the product. From this point, we have our finished steel product. Now a crane comes in and picks up several bundles of steel and moves them either into our warehouse storage area or directly onto a truck or train for immediate delivery to our customer. The inventory of our warehouse is maintained in specific locations and is tied right into our tagging system. Each size of product is produced according to a schedule, which is based upon our different roll mills' crew shifts or turns, with the average product being produced between 6 and 8 times per year. Customers can purchase materials from off the warehouse floor or directly off the production schedule. Nucor Steel, Utah takes great pride in supplying quality steel products both on schedule and delivered on time. Product quality is a top priority here at Nucor Steel, Utah, and it is here at our furnaces that our quality control program really begins. Our personnel monitor the molten metal bath temperature and take samples of each individual heat for its elemental composition. Once cooled, these samples are sent via a vacuum tube system, similar to the one at your local bank, to our quality assurance laboratory. Once in the laboratory, the sample is turned into a coupon through a grinding process, and the coupon is evaluated using a spectrometer. The laboratory personnel have the final say before any batch or heat of steel is released from the furnace area to our caster area. Once at our caster area, additional quality control samples are taken, necessary metal alloys are added, and any additional modifications made. All the while, quality control samples are reviewed by our quality assurance personnel. Again, our analysis laboratory personnel will have the final say in allowing the contents of the ladle to be cast into a billet. Our billets are also monitored for their shape and surface quality. In order to maintain a high-quality intermediary, Nucor Steel Utah has installed an entire water cooling and quality system devoted solely to our caster unit. The quality of our product is constantly reviewed while it is being made in the roll mills. Operators are checking bar dimensions, pattern sharpness, and surface quality. In addition, actual samples of the product will be taken from the cooling bed and within our quality assurance laboratory, tested for both physical properties such as tensile strength and chemical properties such as elemental carbon or magnesium content. Now you have seen how we recycle discarded metals into our high-quality steel products. Steel is the most recyclable, and it's the most recycled product that man has yet to produce, and Nucor Corporation is proud to be a part of this essential service. Nucor Steel Utah is committed to the safety of our employees and protection of our environment. We employ only high-quality personnel, from our front office right into our production personnel. In addition, we make every effort to make the tools available to do all of our jobs as safely as possible. Environmentally, we closely monitor emissions, use closed water systems, and closely control our baghouse system. Quality products, in combination with quality personnel and superior service, is what we feel keeps our customers loyal to Nucor Steel, Utah.